Hello, my friends. Welcome to the class. Thank you for joining on time. This is Bhavdeep. I live in beautiful Chandigarh. Many of you already know me. So I'm going to give students 30 seconds to join because I can see many more students are joining right now. Really good to see. The class is being recorded. If you miss any part of it because of technical issue, internet down or whatever, power cut, you can always see that later on. But try to be online as I'm teaching you right now. Another 15 seconds, we are going to get started. Thank you to everybody who joined on time. Many of you already know me. Some are new maybe. So I'll introduce myself before we get started. A beautiful quote here. If it is important to you, you will find a way. If not, you're going to find an excuse. And that's so very true. Right? So today's session is about photoelectric effect problem solving in JEE. So let me first introduce myself to students who are new here. This is Bhavdeep saying I live in Chandigarh, the beautiful Chandigarh. I did my master's from IIT Bombay in 1998. So most of you were not born, and as I say, most of you because there are some parents also watching the video here. There are some not everybody is 11th or 12th grader. There are many people who are much older and they watch the videos here. So everybody is welcome here. You can call your parents also if you want. Um, I started working in software industry, and then I was always teaching part time. But then 5 or 6 years back, I decided it's a teacher inside of me who wants to be a full-time teacher. So I gave up my job. For past 5 years, I've been teaching with a full-time physics, and for past 3 years, full-time with Vedantu. I've shaped thousands of successful careers. When I say careers, I don't just mean the jobs. I mean, there are students who want to pursue physics, like they want to do physics, PhD in physics, so just want to learn physics for whatever reason. So that's also another thing that I deal with. Many students come here to learn physics with me. They don't have any curriculum. They just want to learn part of something from the world around them. So I love physics, I love kids, and I love teaching physics to kids, and that's the reason I'm sitting right here in front of you. My mission is to make students fall in love with physics. So you cannot enforce love. As I always say, I try to make the classes interesting, and eventually I receive many comments from my students or their parents. The student was like physics was not the favorite subject, and now this is the student wants to do physics, and that really makes the day for a teacher at least, right? So let's start with आज का agenda is obviously photoelectric effect. We are going to squeeze in as much as we can within 45 to 1 minutes to 1 hour. The topic of today's session is problem solving, but before we solve any problems, we have to get in-depth understanding of the theory. So I'm going to spend roughly 10 to 15 minutes covering the theory, and then we are going to do some questions on that. And maybe we'll cover more theory than numericals, but that's a base, that's a foundation of that. Right? And the fun is going to be throughout the session. So let's get started with what is photoelectric effect. So some of you already know it, others may not know it. So let's say there's a piece of metal. I don't have a metal here around me. Let's say this was a piece of metal. So this was a piece of metal, and if I throw some light on that, in certain situations you would actually notice electrons start coming out of this metal. So what's going on? I mean, why do electrons come out, and how do we control the electrons coming out? How do we increase the number of electrons coming out, or how do we increase the speed with which they are coming out? That is all covered under photoelectric effect. So in short, a free electron can be ejected if enough energy is supplied. Now that energy may be thermal energy, right? You don't have to provide light. I mean, those electrons want to be freed. You can provide thermal energy. You can provide other forms of energy. But today we are covering providing energy in the form of light. A light photon falls on electron, and electron becomes free, and that is called photoelectric effect. Before we start understanding photoelectric effect, we have to go through the big debate that was going on for years and years. Humans knew light it's a form of energy, but there was a big confusion whether it is a light is a particle or a wave. So, long story short, Newton started by saying light is particles, and he was able to explain the phenomena that we know about light, like reflection, refraction. He was able to explain them, taking example of an elastic ball. You collide with the wall here, assuming no friction, no moment, no laws in energy, as in 100% elastic collision, you would actually see the angle of incidence of the ball is going to be equal to angle of reflection of the ball, right? So light is particles, and that's what everybody believes because he is Newton and he is explaining things logically. Then came the famous Young's double slit experiment, and that showed light shows some phenomena which cannot be a particle phenomena, namely interference. So he was able to show, and actually he found it that light shows interference kind of behavior. So two light rays or two light waves actually interfere constructively, destructively, and also there were other phenomena that light shows like diffraction of light, polarization of light. These are not the things typical of a particle. You don't have particles showing diffraction, right? So that's something like wave. And so Huygens and Thomas Young, these guys, they believe light is wave. But then when they're proposing light is a wave, you got to also prove, also show how a wave is reflected. So whatever Newton was able to show with particles, they show with waves. They say light is a wave, and this is how the angle of reflection is equal to angle of refraction. This is why Snell's law is followed in case of refraction. Plus, we are also able to show you why there is an interference pattern, there is a diffraction, polarization. Okay, Newton made a mistake. It's not particles, it is wave. Right, so end of the story. But now it's not it, because now there were two phenomena that you could not explain if you assume light is a wave. The first one is photoelectric effect, right? The second one is Crompton effect, right? So we are not able to show that, and that comes then comes Mr. Einstein. He says it's both. I mean, that's something new, because how can something be particle and something be wave at the same time? And the next slide we are going to cover what is a wave and what is a particle. But Einstein is proposing, oh, it's both. It's not like it is wave at some point of time, particle at some point of time. At any given point of time, it is both a particle and a wave. It might show wave-like behavior in certain scenario and particle-like behavior in certain scenarios, but it is both. Then came Mr. De Broglie. De Broglie says everything is a particle and a wave. So namely this pen here, it's a particle, right? Particle doesn't mean tiny particles. Particle is what we are going to see in the next slide. So De Broglie is proposing, okay, this being a particle is also a wave. Me sitting here, I am a wave, right? So those are the things we are not covering in today's session, but that's dual nature of everything. So let's first understand what is a particle and what is a wave. So particles are localized. So this pen or this mobile phone in the picture, it's sitting, it's here, it's localized, right? Localized as in it has a certain position in time space. I can say, I can take some origin and specify x, y, and z coordinates of that. Wave is delocalized. So think about a wave, this wave. So where is this wave? Is this wave, let me use the colors here. Is this wave here? Is this wave here? Is this wave here? Is this wave? No, it's everywhere. In a given region, the wave is everywhere. It's not localized. In a given region, when I'm speaking, my sound waves are everywhere, right? So it's not like this is one wave, this is another wave, this is one wave, it's everywhere. So waves are delocalized, whereas particles are localized, right? Now, when this thing occupies this space, it's not like another thing can occupy the same space. You can put it on top of it, but then that the z coordinate or y coordinate has changed. So same space cannot be occupied by multiple particles. Where are two or more waves can coexist in the same space, and we know that when they do that, they exist in the same space. They interfere. They either constructively interfere or destructively interfere, right? So resultant wave can be larger or smaller than the individual wave depending on how they interfere. But the number of particles in a space, so let me define the space as my palm of my hand. So there are two particles here. So 1 plus 1, 2, right? So you add those particles. Whereas in the case of waves, you actually, they add up, or they reduce the magnitude of each other, right? So that's called interference. So that's the basic difference between what is a particle and what is a wave. With that definition, as I'm sitting on this chair, I am a particle, but now Debro is saying I am also a wave, right? That's in some other webinar. Definitely we are going to cover that, but for now let's focus on what we are focusing on. Light is was supposed to be a wave, or what assumed to a wave, but now Einstein is saying, oh, it's both of them. So it's both a wave and a particle. Now, but why do we care? Right, so why do we care whether, and we have already covered this, because the problem is, if we consider light as a wave, you cannot explain why photoelectric effect happens the way it happens. So there are a few things, I mean, I don't have time to cover in detail. I'm going to cover as much as required for your JEE. At least it's more like a crash course here. But let's say you assume light is a wave. Right, and we know how waves behave. So what is the intensity of wave supposed to mean? What is the amplitude supposed to mean? So I sit down with a pen and paper and say, okay, if I increase the intensity of wave, this is what is going to happen with the photoelectric effect. If I change the color of the light, this is what it should happen. And I list down all of those. And then I go to the lab and try to perform the experiments. The results of the experiments are completely opposite. It's not like a little difference here, it's completely opposite. I was expecting more electrons to be ejected. There is no change in electrons, number of electrons. I was expecting electrons should have more energy. It doesn't change, or it is less, or whatever, right? So you cannot explain photoelectric effect. Another is Compton effect. Sorry, Compton effect is this. I'm not covering that today. So let's say there is an X-ray. So X-ray falls on electron, and what you see, the X-ray that comes out after collision there has a longer wavelength, and that's something you cannot explain with the wave theory. So again, I repeat, there is an X-ray that collides with an electron. Electron moves in one direction, and obviously momentum is conserved. That is why if electron goes this way, the X-ray goes this way. But then if X-ray goes this way, its color has changed, its frequency has reduced, wavelength has increased. I mean, that's nothing, this you cannot explain with the wave nature. On the other hand, if you consider light as a particle, you cannot explain things like, as I already covered, interference, diffraction, polarization, Doppler's effect, scattering, right? So, and that is why we care. Now, if we assume we understand light as both particle and as a wave, and as Einstein is proposing, we can explain everything, and that is why we care. So let's understand a little about photons, and then let's get started with the photoelectric effect. So photon is, as Einstein is proposing, a packet of energy, right? So we say, okay, light is traveling as a wave, but then you can assume, and this is a wrong representation, by the way, because as you will see, this is more like an overly simplified, plus the way we visualize the world, right? You can visualize these as packets of energy. So these are not particles in the sense like electrons, protons, or dust particles. These are purely energy. They don't have any rest mass as such, right? So these are packets of energy. Each of the photon has this much of energy, where h is the Planck's constant. It's a tiny little number, 6.626 times 10 to the power minus 34 joule seconds, and multiply by the frequency of the light that you're talking about. So this is the amount of energy that is in one photon. Right? The momentum, on the other hand, many students get confused here, because what we have studied is momentum is mass times velocity, but that is Newtonian physics, and that is valid only for things traveling with slow speed, the speed in the world that we live in. So when you approach the speed of light, all these things that you study in Newtonian world are no longer valid. So momentum actually is going to be energy divided by the speed of light. So let's see that energy by c. So that comes out to be hf by c, or you can also write it as h divided by the wavelength, right? So a photon has energy equal to h times the frequency, and the momentum equals to h divided by the wavelength of the light. And these are tiny little numbers, very, very little numbers, right? So even though the photons are falling on my palm right now, they're reflected back. So if there was a tennis ball here falling on this, reflected back, the rate of change of momentum is going to be the force experienced by the palm. But in this case, the energy or the momentum is so tiny that zillions of photons are falling on my palm, but I don't feel the force as of now. But the force is not zero. Okay. So again, something that we are trying to deviate from this main topic today is photoelectric effect. So this is exactly what happens. As you can see, if you throw some light on certain metals, electrons, you can see those tiny little electrons, they are emitted, and they are emitted with some energy that we will see depends on the color or the frequency of the light here. So photoelectric effect, in short, is photo means light, electric means electric current, right, or electrons. So when you throw light on certain metals, what would happen is electrons start coming out of it. And look at the video here, and that is going to be an electric current here, because electrons reach here, electron complete the circuit. That is exactly what is happening here. Okay. Now behind the scenes, what happens? So let's understand what is happening. This is a big picture, like macroscopic picture. Let's have a supernatural powers, and let's say I am able to view the electrons, right? Obviously that's not possible, but let's say there are some electrons here, black color electron, red color electron, green color electron. Okay, so these electrons, colors don't mean anything, it's just for easy explanation. Now, you know, electrons in a metal, they are free electrons, right? They keep moving. I mean, obviously this electron here, it's not like sitting there, it's actually moving in random directions, right? But then when it's moving in random directions, wouldn't you think, okay, it also briefly comes out? It's moving in random direction. Maybe it has a velocity in this direction. Newton says it should keep moving in that direction unless it experiences some force, some collision, something. So it keeps moving in that direction, it comes out of the metal. But then that is a very brief kind of free space it has received, because what would happen now is, as it comes out, this metal becomes positively charged. Right? It pulls it back, come back. Right? It's more like a dog on a leash. So yeah, you can visualize it like this. So there's a dog on a leash. Okay, I'm really poor with making pictures here. I don't know how to make a dog. Seriously, I don't know how to make a dog. Right. So let's say there is a dog here. Right. So now the dog can roam around briefly, but then it has to go back. It cannot run away. It can come out briefly and then comes back, goes back into the house, but it doesn't have enough energy to break that chain and just run away. And that's exactly what is happening here. Electron can briefly come out, but then it cannot just run away. It needs, maybe if you provide some energy, it can run away. But as of now, electron is coming out briefly and then it goes back. Now, what if I provided some energy? How do I provide energy? I can heat it up. Thermal energy, right? Thermal energy is thermionic emission. This electron will become free and just go away. And this is thermionic emission. Or there are other ways also, field emission. What if you provide a very strong positive field here? This electron will get attracted and it will run away. So this is field emission, but we are focusing on photoelectric effect. I'm just giving brief overview of what other methods do we have. So let's say there is a photon here, and photon falls on the electron. It gives it some energy, but then it's like electron needs certain minimum amount of energy to become free. So let's take, for the argument's sake or for the understanding sake, that this electron, let me wipe this out, this black color electron needs 3 electron volts of energy. Okay, everybody understands electron volts. I'm hoping that you understand what is electron volt. It's a unit of energy, and we use that at such tiny levels where joules actually is not humanly understandable, right? It will be such a small number, you don't understand. You're not able to compare that. All right. So now let's say this electron needs 3 electron volts to become free. Now there is a photon, let's say a photon of some light, right, red light, and it has 2.1 electron volts of energy. Now this electron is useless. It's like, sorry, this photon is useless because electron needs 3 electron volts. Now this photon only has 2.1 electron volts. It's of no use. electron is going to reject this. Now many students ask a question, and that's a very good question. What if two of these electrons come together and they have enough energy now? So what if this electron takes two photons? What if two photons combine together and become 4.2 electron volts, and that energy is more than enough for this electron? But that doesn't happen like that. One electron, one photon. So photon will take so electron will take one photon or no photon at all. So I'm going to repeat that. Electron will take one photon's energy and become free, or it will say no thank you. It is not going to take two or more. It's just one electron means one photon. So this photon will be useless, and it moves on. I mean, it's useless. You can't do anything with it. Now let's say there's another color light, I don't know, maybe green color light, and it has 3 electron volts. What would happen now is this electron needs 3 electron volts. This photon has 3 electron volts, and remember, photon is purely packet of energy. So this photon's energy is taken by this electron, and this electron becomes free. It comes out of the metal, and it is a free electron was free electron within the metal. This is completely free. It can roam around in the outside space now. Now, what happens if the photon has 4 electron volts? If it has 4 electron volts, the electron will use 3 electron volts to become free, but then it will have 1 electron volt of extra energy, and it has that much of kinetic energy. I'm going to repeat this because this is the basis of all the questions that you're going to do. The analogy here is this, and this is what you might have done in grade 11th in detail or might not have done in detail. Depends on how you studied. So I'm going to repeat it, and I'm going to take 1 minute on that. So something, and obviously this is not to scale, so this is Mother Earth, and I'm standing on the earth with this pen. Right? Now I want to throw this pen, if it goes away, and then assuming there's nothing around it, no other planets, nothing, the pen goes. As it goes, the gravitation of the earth is still pulling it, and then if there was nothing around, the pen would come back. So pen goes, but then it will return back. Maybe long time, but then it will definitely come back. I want this pen to go to infinity. I want this to reach to infinity. You have already done the escape velocity in the previous class. So escape velocity is the velocity that you need to give this pen so that it goes to infinity, and it comes out to be 11.2 kilometers per second. Note that this is per second, and it's a huge velocity. So if I throw this pen with 11.2 kilometers per second, and infinity is obviously not real, it's like a conceptual kind of infinity. You're not going to reach there, right? Wherever you reach, it's not infinite long, but then let's say it reaches infinity, and this pen, which is an object, let's say it reaches infinity, and then it stops there, because it has used all that kinetic energy I gave it to overcome all this force of attraction. And there are many different ways to visualize that, but I'm just doing it a little faster. So it takes that energy, reaches infinity, and stops there. But what if I give this another ball here? Maybe I give it 15 kilometers per second. Right? I'm giving it more than required. So what would happen is it will use that kinetic energy equivalent of 11.2 kilometers per second to reach infinity, but then it has some energy left, which is kinetic energy. So the first ball, which received 11.2 kilometers per second of energy, worth of energy, is going to stop there. Right? I know this is a velocity here, but half mv square is what I'm talking about. So half into mass of this pen times all this meters per second velocity is squared. So the thing which we receive enough energy to just go to infinity, it goes to infinity and stops, but this one has still some left over, and that is why it is still going to keep moving at infinity. And this is exactly what is happening here. So if it needed 3 electron volts, if I provide 3 electron volts, it is going to become free and then stop. Because as it is going away, the positive ion here is going to pull it back. So it slows down and then stops. But if I provide more energy, it has some kinetic energy left over there. So what happened just now is energy of photon is equal to whatever energy required to become free here, which we'll call it as work function, we'll see that, plus the kinetic energy that is left over. Okay. So let's recap all that we did here in a little easier words there. So what I'm saying now is, I'll do this one more time. So there was some electron here which I painted black, and it needed 3 electron volts. But then there was another electron here painted blue. It will need more energy because it has to come to surface and then become free. So this electron which was deep inside the metal might need 4 electron volts, and there's another electron which is deeper inside the metal might need 5 electron volts, and these numbers are for easy understanding, right? Now, what is the minimum energy for this metal that is needed for photoelectric effect? That minimum energy is 3 electron volts, and that is what you call the work function of this metal. So work function is the minimum energy that you need for a given metal. Iron का कुछ होगा, copper का कुछ होगा, nickel का कुछ होगा, cesium का कुछ होगा. So every metal will have a certain number assigned to that. That is called the work function, and that is the amount of energy you need for these surface electrons to become free. And that is called the work function for that metal. So in the given example here, the work function for this metal is 3 electron volts. Please remember, this is a property of the metal, of a given material out there. Okay. So what that means, why do we care about this number, is because any photon which has the energy less than this number is useless for me. So if there is a photon that has 2.9 electron volts, it is useless. It is not going to have any photoelectric effect here. Okay. I need a photon with at least 3 electron volts. So let's say I have 3 electron volts of photon here, one photon with 3 electron volts. So I choose such a photon such that energy is equal to h times the frequency, and when I multiply these two numbers, I get 3 electron volts. So I choose a frequency of light that is equivalent of 3 electron volts. Okay. So when this photon comes in, the black electron becomes free, and that is it. It becomes free and it stops here. But then let's say I have another photon, and that photon was, let's say, 4 electron volts. तो इसमें क्या होगा? 4 electron volts में black electron comes out, becomes free, and also has kinetic energy of 1 electron volt because it has leftover energy now. Blue electron will also come out, but then it will stop. It will not have any energy there. ठीक है, मैं एक बार और कर देता हूं. So let's say instead of 4 electron volts, this time I have 5.1 electron volts, let's say. है ना, कोई photon लिया which has 5.1 electron volts. Now you do the math. 3 electron volts is used by the black electron, but then it has 2.1 electron volts of kinetic energy. Now when you're talking of blue, it has 1.1 electron volts of kinetic energy, right? And then the green one also has some kinetic energy, which is 0.1 electron volts. But you can see the maximum energy is possessed by the surface electrons there. Okay? So that brings in the famous equation given by Einstein, obviously, and this is conservation of energy. This is nothing more than law of conservation of energy. So what we are doing in this case, I'm also watching the time so that I don't take more time than I have promised you. I'll make you free on time. So photon had some energy, right? So that energy is taken by the work function needed. Okay, that 3 electron volts was the work function, but the leftover is going to be given as the kinetic energy. But we are talking of maximum kinetic energy because remember, work function is the energy needed by the surface electrons. अंदर के जो electrons हैं, they will need more work, more energy to become free. So they will have less kinetic energy. So please pause the video if you are watching a recording here, or otherwise maybe come back here and see this equation. This is the only equation that you need here. So photon energy is used up to release an electron, that is the work function for the surface electrons, and plus the kinetic energy that is left over. So let's see that in action. First of all, work function, as I said, it depends on the material. So here are some sample materials. So lithium has a work function of 2.9. Now let's compare this. So let me move the camera or the video here. Let's look at lithium. So now if you're going to shine a red light on lithium, red light doesn't have enough energy to release an electron. Similarly with orange, yellow, right? None of them. So you have to go to the violet region, and then some kind of violet light which has a frequency such that the energy of a photon is more than 2.9 or equal to 2.9 is going to release an electron. So if you shine violet light on lithium, you will see the photoelectric effect happening there. Look at cesium. Cesium has only 1.9 and red light is enough for that. Right. So now if you look at more like copper, look at copper. Copper has 4.6 electron volts of requirement. Even violet light is not enough. So if you were to have photoelectric effect with copper, you actually need ultraviolet light. Okay. So this is how it works. So this number on the left, work function, tells you what is the minimum energy that is needed to release an electron. And now you go to the chart here and see, okay, which light. I mean, even red is so many frequencies in red, right? So you see a particular frequency which has at least that much of energy, and that is governed by the photon's energy equation, that is equal to h times the frequency. That is the energy of a photon. Okay? And that is being used here to create this table. That is being used. Now, few things before we start doing the questions, and this is where most of the students make a mistake, and this is why I have summarized everything here. This is the summary of the things that I have seen over past many years of teaching. Many students go wrong with this. One electron, one photon, as I was saying. Right. So if 3 electron volts is needed, you cannot say I will take 2 electron volts of photon and another one of that, combine them to make 4 electron volts and give it to electron. You cannot do that. Right? So one electron will take one photon or no photon at all. Now this table gives you a summary of like what is controlled by each of these parameters of light. So when you're talking of frequency of light, that frequency of light controls the energy of the photon, because energy is h times the frequency. So when we are changing the color of light, we are actually changing the frequency. So red light has the least frequency and it has the least energy. You go to orange, it has more energy. Green has more energy, violet has more energy. So frequency of light controls the energy. More the frequency, more the energy. Keep it in mind. Okay. Secondly, intensity, and this is why the wave theory failed. And in the upcoming classes, maybe we'll cover in detail about that also. But for now, intensity of light. What is intensity of light? It's the number of photons. See, intensity is energy. And the definition of intensity is energy per unit area per unit time. If you're increasing intensity, you're actually increasing photon ki energy the same hai na. If you have a red color light, photon's energy is not increasing. So this energy can be summation of all those photons falling on my palm, maybe, right? So if you increase the intensity, what is going to be the number of photons striking per unit time there? Okay. So please do remember, intensity of light controls the number of photons falling on this. So more the photons, more the electrons that can be released. Think about that way. Let's say you have chosen a light which is a blue light maybe, and it is having energy enough to release the electrons. Now what? What if you increase the intensity of that blue light, the same color light, but you increase the intensity? So more photons are falling on this, and that means more electrons will be released. So the current will increase, the electric current will increase. Now work function of a metal is the property of the metal. So this is more like how easy it is to release the electrons. If work function is small, so then it is so less energetic photons can also release the energy. है ना? So आगे बढ़ते हैं. अब क्या है इसमें? Let me move the. So practice makes a perfect, and this is where we start doing the questions here. So any doubts, please revisit the video that was before this, because the questions are purely based on this thingy plus the Einstein's equation here. This equation and this page is all you need to do most of the questions. Okay, so practice makes perfect. Let's start with the questions now. Yeah, please answer the question. Photons emitted by a source of light do not all have the same energy. Is the source monochromatic? Now I am getting questions here, sir. What is monochromatic? See, monochromatic is one color, one frequency light. You have studied that in your optics class, right? So monochromatic means purely one frequency light. Thank you for the responses there. So photons emitted by lights do not all have the same energy. Before I answer that question, let's see what's going on here. So there is a metal here and there are photons here that's falling on this. Now it says some electrons come out with more energy, let's say 1 electron volt. There's another one which is coming out with 2 electron volts. Now don't you think these photons had different energies, and that is why electrons, see, there are two ways to look at it. So let me explain completely. So maybe this electron which came out as 1 electron volt of energy was the surface electron, and this was deep buried inside, and it had 0.8 electron volts, let's say, right? Because it needed more energy. So maybe the photons are having the same energy, but then the electrons were either surface electrons or inside electrons. So in that case, okay, it is monochromatic, but may not be monochromatic. How do we know? Because see, what if these are both surface electrons and this electron, so let me take a better example here, sorry. So what if this electron needed 3 electron volts and this electron needed 3 electron volts, right? So this one had 4 electron volts of energy and this one had 4.5 electron volts of energy. So this electron will come out with kinetic energy of 1 electron volts, and this will come out with kinetic energy of 1.5 electron volts, because of the fact that these two photons itself had different energies. So it is not guaranteed that it is a monochromatic source of light. Okay? So next questions karte hain. We have 5 or 6 questions here. Yeah. So I'm already getting so many responses here. Which colored light bulb emits photons with the least energy? Yeah, obviously it is governed by the equation energy is equal to the Planck's constant times the frequency. Now if you look at the spectrum there, the frequency is least for the red color light. Frequency is least, and that is why the least energy is the red color. Okay. Pure violet is more energetic, it has more frequency. Ultraviolet is more energy. X-rays are more energetic. Gamma rays are super duper energetic. Okay, so please do this question. I think this is cut off a little. Yeah, now you can read it. Yeah, I can already see students answering there. Thank you for that. Yeah, so there is a light bulb here, and that's giving out red photons. When you increase the wattage or the power, intensity is equal to power per unit area. Now power is governed by the intensity of light. So that should give you a clue. More power means more intense light. More intensity means क्या बोला था मैंने? More intensity means more number of photons. So more intensity just means more number of photons. If the frequency is same, energy is same. So no. Right? Because energy is equal to h times the frequency, assuming this is the same red color frequency. The frequency is not changing, energy is not changing. What is changing actually is the number of photons coming out. Each photon still has the same energy in electron volts, but the number of photons coming out per second has increased now. ये करो. This is JEE question. JEE means question. So let's do this question together. एक बार इसका फोटो बना लेते हैं, बिकॉज पिक्चर्स स्पीक 1000 words. So this is illuminated by a photoelectron, right? 400 nanometers of light. Okay. Now there is an electron that comes out and it has a kinetic energy of 1.68 electron volts. Simple enough. There's nothing much to do here. We know the famous equation h times the frequency of light is equal to the work function plus the kinetic energy max. है ना? अब इसमें क्या क्या दिया हुआ है? ये this phi is unknown. hf हमको नहीं पता. HF हम कैलकुलेट करेंगे, बट फ्रीक्वेंसी की जगह वेवलेंथ दिया हुआ है. सो आई नो, सी आई विल डू ऑल द स्टेप्स बिकॉज सम स्टूडेंट्स विल नॉट गेट इट. सो स्पीड इज इक्वल टू फ्रीक्वेंसी टाइम्स लैम्डा. तो ये यहाँ सब्स्टिट्यूट कर दो. इसको सब्स्टिट्यूट किया तो फ्रीक्वेंसी क्या हो गया? c बाय लैम्डा, है ना? h c बाय लैम्डा इज इक्वल टू द वर्क फंक्शन प्लस द काइनेटिक एनर्जी. अब ये देखो, दिस इज अ शॉर्टकट दैट मे बी गिवन टू यू, मे नॉट बी गिवन टू यू. सो प्रोडक्ट ऑफ HC इज 1240 इलेक्ट्रॉन वोल्ट्स नैनोमीटर्स. अब तुम यूनिट्स भी देखो अगर इसके, सो गो बाय द यूनिट्स. लेट्स सी दैट. एक बार कैमरा अपनी फोटो यहाँ कर देता हूँ मैं. तो HC, प्लीज डू रिमेंबर दिस नंबर. दिस इज गोइंग टू सेव यू अ लॉट ऑफ टाइम. अदरवाइज यू आर गोइंग टू प्लग इन द Planck's constant, you're going to plug in the speed of light, you're going to spend unnecessary time in calculation. This is one of the numbers that I ask students to memorize, and please also take care of the unit there. That's in nanometer. If it was in angstrom, it would be different. It would be 124. तो अब यहाँ पे रख दिया 1240 इलेक्ट्रॉन वोल्ट्स टाइम्स नैनोमीटर. अब नीचे भी नैनोमीटर आ रहा है, देखो 400 नैनोमीटर. तो नैनोमीटर नैनोमीटर क्रॉस, what you get is electron volts, है ना? So is equal to, let's complete the equation before we work on it, is equal to 5 plus kinetic energy is also given in 1.68 electron volts, है ना? कितना ब्यूटीफुल इलेक्ट्रॉन वोल्ट्स हो गया. अब ये 2 जीरो कट गए, so this is 3.1 minus 1.68, तो ये 2 बचा, 4 बचा, 1.42, right? 1.42 bacha, which is very close to being 1.41, and that is your answer. Electron volts. Okay? So please do remember, this is going to save a lot of time in competitive exams at least, and also in your board exams. HC, the product of HC is 1240 electron volts nanometers. उसको याद रखना, unit नहीं बोलना. ठीक है? Let's try this. This is another question from JEE mains exam. This is 2016 exam. Very nice question, very easy question also. ठीक है, तो इसको मैं बता देता हूँ कैसे करना है विद ऑल द स्टेप्स, बट यू आर सपोज टू डू इट लाइक दिस. ऐसे फटाफट हो जाएगा. एक बार समझ में आ गया पैटर्न क्या होता है. पैटर्न नहीं, मतलब ये तो कॉमन सेंस से ही करना है. You always start by the equation given by Mr. Einstein. So HF is equal to the work function plus the kinetic energy, है ना? यही तो है. अब इसमें काइनेटिक एनर्जीज की बात हुई है, द मैक्सिमम काइनेटिक एनर्जी. सो रीअरेंज कर लेते हैं. काइनेटिक एनर्जीज HF माइनस 5. ठीक है, ये आ गया मेरे पास. अब देखते हैं, देयर इज अ फोटो इलेक्ट्रॉन. तो इसकी जो है लैम्डा से जब आया, सो k lambda means the kinetic energy when lambda was falling on it is equal to hc by lambda हो गया ना. hc by lambda, hf की जगह c by lambda लिख दिया, माइनस द वर्क फंक्शन. ये हो गया. अब काइनेटिक एनर्जी व्हेन लैम्डा बाय 2 वाज फॉलिंग इज इक्वल टू hc बाय लैम्डा बाय 2 माइनस द वर्क फंक्शन. ये हो गया. अब उन्होंने क्या कहा है कि इफ द मैक्सिमम काइनेटिक एनर्जी ऑफ द फोटो इलेक्ट्रॉन्स इन द सेकंड केस इज 3 टाइम्स. तो उन्होंने ये दिया है मुझे, लाइक ये जो सेंटेंस है, दिस सेंटेंस in English will be converted into mathematics. So all they are saying is this energy is equal to the 3 times of the energy that was released earlier, because the wavelength is reducing, frequency is increasing, so kinetic energy is obviously increasing. ये equation है, इसमें plug in कर दो यार. So left side में आ गया hc by lambda by 2 का 2 lambda इधर बन गया ना, 2 ऊपर चला गया, minus 5 is equal to 3 times of hc by lambda minus 5. अब this is a piece of cake. It's the basic algebra you studied in 6th 7th grade. अब इसमें क्या आ गया, 2hc by lambda, सिंपली कर देता हूँ, hc by lambda minus 5 is equal to 3hc/λ माइनस 3 फाइ है ना, वो बस 3 को डिस्ट्रीब्यूट कर दिया। अब ये 3 फाइ इधर ले जाओ तो 3 फाइ माइनस फाइ क्या बन जाएगा, यहां से मैं लिख रहा हूं यहाँ पे 2 फाइ इज इक्वल टू 3hc/λ माइनस hc/λ इज hc/λ। तो वर्क फंक्शन कितना आ गया, hc/2λ। फाइ पता करना है हमको, that's all, you're done, it's over। So this is the equation, this is the it's just the conservation of energy, there's nothing you have to memorize also. Energy given, some of it is used to free the electron, the rest of it is kinetic energy, conservation of energy। See this equation, Bernoulli's equation, or first law of thermodynamics, and there are so many things, Kirchhoff's second rule, all these are conservation of energies rewritten in a different way। Very easy question, very easy question, yeah। Okay, I can see many responses coming in and some are making the same mistake, I can see that। एक बार और revisit करो question को, it's very very easy। So एक फोटो बना लो, एक reflecting surface है, reflecting surface as in mirror, right? एक फोटोन आ रहा है, एक फोटोन वापस जा रहा है, सेम फोटोन वापस जा रहा है, it's like collision, like 100% elastic collision, perfectly reflecting surface, right? So energy E, so remember we said okay momentum is energy divided by the speed, right? वो शुरू में ही करा था मैंने, बहुत पहले ही करा था, ये 20 सेकंड स्लाइड है, कहाँ करा था मैंने, see somewhere down here we covered this, right? Momentum is energy, and obviously energy is, see momentum is equal to mass times velocity, those things work with when I'm running, when the car is moving, a jet plane is flying, but those things are not true. I mean, those are approximations in the world that we live in and see the things around us. That's Newtonian mechanics, that's classical physics, right? That's not relativistic physics, and that's going to take in effect when you talk of this things traveling close to the speed of light, and this is the speed of light because this is light, right? So momentum कितना है इसका, E by C, इसका momentum कितना, many students make the mistake here and they say okay इसका भी तो E by C होगा because it's going back with the same momentum, but इसका negative E by C है ना, because look at the direction has changed now, right? Now what is the change? Change is equal to final minus the initial, right? That's what you call a change, है ना? So final कितना है, minus E by C, है ना? Initial कितना है, minus sign लिखा है because there's a formula here and the initial is E by C, so total change हो गया minus 2E by C। अब ये minus का क्या करें? See the momentum transferred to the surface, this is the momentum given to the photon, momentum can neither be created nor destroyed, so the photon has received this much, the wall has received this way, plus 2E by C। Okay, so this is the answer, 2E by C। Please do remember momentum is never destroyed, if you throw a ball on the wall, the ball is coming back, so it has a change in momentum, but the wall along with the earth has started moving forward, but because of the huge mass, that momentum means a very tiny velocity in there। ठीक है, तो यहाँ तक clear है सबको? Yeah, many students are saying ultra easy, it was easy, right? So now just stay for 2 more minutes before you leave. This is just obviously some FYI, you don't have to join this. We covered in 45 minutes to 50 minutes today whatever we could. There is an upcoming 2-hour class, but that is a paid class for 99 rupees. I mean, it's not a big amount, maybe it is a big amount, I'm sorry, I'm not saying it big amount or small amount. So the class is 99 rupees, that is 2-hour class, what we are going to do in that. So because we had 45 minutes today, I have given enough information. It's not like I did not cover things. I tried to cover everything today. What I could not cover today were the graphs and all. So those are the things, plus we'll do more detailed questions in there. We'll carry over what we studied today and we'll carry over to that. So that is upcoming Thursday, 24th of October, 9 to 11 p.m. 2 घंटे की class, right? So this is the link. If you want to enroll, please do go to this link, or you can go to the same link you were enrolling for this today's session. There also you'll get it, or you can call Vedantu for that. So the class is 1900 rupees for 2 hours. This is just one class. It's not like every Thursday. It's one class. So what can you expect from that is, first of all, yeah, let me say, yeah, photoelectric current, like these kind of graphs we are going to cover, because we did not cover the graphs. Obviously photoelectric effect is a bigger topic, so we have tried to cover whatever we could, and this is going to definitely benefit you. Today's class was definitely beneficial. Many students are already saying thank you sir for that. Yeah, thank you for the good words, by the way. But what I'm saying is we could not cover the graphs in today class. We'll cover graphs and some of the doubts we can cover, not many doubts but some of the doubts. And also we are going to solve more numericals. I'm expecting in that class we'll solve at least if not less 8 numericals, and in depth. I mean, I don't go by quantity. I don't say okay we'll solve 25 questions, we'll solve 7 or 8 questions, but in depth and analyze everything so that you know what to do there. Okay. So here is the link. If you need that again, note it down, or you can call Vedantu help desk. They can help you, or you can go to the same link that you registered today. Click on that. You will see the link for the upcoming class. So as I always say, I never say goodbye. I say see you soon, either in the session that I told you, or maybe in one of the free upcoming webinars. So it was nice talking to you. I hope, and thank you for the good responses that I can see on the chat box. Yeah. See you soon. Bye bye.